he has another claim, which is that he solved the second law of thermodynamics. And from my reading of it, I wasn't able to see what the problem was with the second law and how it was solved, other than you say you derive it from statistical mechanics, which was there before. I must be missing something, because I don't imagine Stephen would make that claim without there being something more to it. So please enlighten me.
Yeah, okay. So I think, as with many of these things, that blog post about that series of 3 blog posts about the second law, I think was there was interesting, just like with NKS, right? I think there was a lot of interesting stuff there that got figured out. It wasn't quite as grandiose as I think Stephen made it out to be. But again, that's the responsibility of any scientist, right? Is to slightly inflate the significance of what they're doing. But so my reading of it is as follows: that so there's a kind of standard textbook popular science type way that entropy increase gets explained, right? Which is you say if you define entropy as being the number of microstates consistent with a given macro state, or the logarithm of that, which is Boltzmann's equation, then the fact that entropy has to increase is kind of obvious in some sense, because the number of ordered states, the number of ordered microstates, or the number of microstates consistent with an ordered macrostate is always going to be smaller than the number of microstates consistent with a disordered macrostate. And so if you're just ergodically sampling, in your space of states, you're going to tend towards ones which are less orderly and not towards ones that are more orderly. And that argument, or that explanation, seems convincing for a few seconds until you really start to think about it and you realize that it can't possibly make sense. And one reason, a very foundational reason why it can't possibly make sense is because that explanation is time symmetric, right? So if it's the case that you're ergodically sampling your space of possible states, you're going to and yes, okay, the less ordered ones are always going to be more numerous than the more ordered ones. Then yes, it's true that evolving forwards in time, you're going to tend towards the less ordered ones. But it's also true that if you're evolving backwards in time, you would tend towards the less ordered ones. But of course, that's not what we observe in thermodynamic systems. So that explanation can't be right, or at the very least can't be the complete answer. And so I think the conceptual problem is a real one, right? I think it is true that we really don't fully understand the second law of thermodynamics from a statistical mechanical point of view, and as soon as you start trying to apply it to more general kinds of systems, the problems become worse. I mean, there's a famous example that was brought up by Penrose of what happens when you try and apply the second law of thermodynamics to the early universe. And again, you seemingly get these two contradictory answers. That so as the universe evolves forwards, if we believe the second law, things should be getting as we get further and further away from the initial singularity, things should be entropy should be getting higher and higher. And yet, when you look back close to the initial singularity and you look at the cosmic microwave background and so on, it looks very, very smooth. It looks basically Maxwellian, right? Or like a Boltzmann distribution. It looks, more or less like a maximum entropy state. So we have this bizarre situation where as you move away from the Big Bang, entropy gets higher. But as you go towards the Big Bang, entropy gets higher. So something must be wrong. And, Penrose has these arguments about conformal cyclic cosmology and how, the role of gravitational fields is essentially to decrease global entropy and all that kind of stuff. But that's all, again, fairly speculative. And I would say at some deep level, that's still a story we don't really understand. So that, I think, is the problem that's being solved. And that series of blog posts proposes, and again, this is not really that, even in NKS, there were indications of this idea. But yeah, the basic idea is that you can explain the time asymmetry in terms of computational irreducibility.
Explain.
Where you say, okay, so even if you have a system whose dynamics are exactly reversible, in practice, because of computational irreducibility effects, they can become, the system can become pragmatically arbitrarily hard to reverse. And that you can think about it essentially as being a kind of a cryptanalysis problem, right? So in a sense, the dynamics of a computationally irreducible system are progressively encrypting certain microscopic details of the initial condition, so that in practice, even if it is in principle possible to reverse from a computability standpoint, if you try and think about the computational complexity of that operation, it's equivalent to solving some arbitrarily difficult cryptanalysis problem to work out, okay, where exactly was that gas molecule at time t equals 0? And that goes some way towards explaining this time asymmetry problem. I don't think it's a complete explanation. I think there's a yet deeper mystery there, but I do think it's an interesting collection of ideas.
Yeah, so that's observer dependent. So it would be difficult for you. Difficult for anyone, but difficult for an observer. But for the system itself,
yes.
Would there still be that issue of having to decrypt for the system itself?
Well, no, I would argue not, because, it's a very important point, right? That these notions are all observer dependent, because in a sense, the Boltzmann equation requires the existence of a macro state, right? Yeah. So, and the macro state is an observer. It's a synthetic kind of observer theoretic idea, right? It's like, you've got a bunch of molecules bouncing around in a box, and so they have some microstate details. But then you want to describe that box in terms of gas kinematics. You want to describe it in terms of a density and a pressure and a temperature and whatever. So, and those give you your macrostates. But the choice to aggregate this particular collection of microstates and say these are all consistent with a ideal gas with this, temperature and this adiabatic index or whatever, that's an observer dependent thing. And so, and that's another point that, again, I don't think it's completely original, but I think has not been adequately stressed until these blog posts, which is that different definitions of an observer will yield different definitions of entropy. Different choices of coarse grainings yield different definitions of entropy. And therefore, in that sense, it's kind of unsurprising that, as von Neumann and Claude Shannon and people kind of pointed out, that, that the term entropy is so poorly understood and that there are so many different definitions of it. There's entropy in quantum mechanics, there's entropy in thermodynamics, there's entropy in StatMech, there's entropy in information theory, and they're all similar vibes, but they're formally different. And you can have situations where one entropy measure is increasing, one entropy measure is decreasing. And that becomes much more easy to understand when you realize that they are all measures of entropy relative to different formalizations of what it means to be an observer. So with regards to the decryption thing, yes, I would say there's an aspect of it that is fundamental, that is purely a feature of the system. That's even if you don't have any model of the observer and you're just looking directly at the data structures, you can have the situation where the forward computation is much more easy or much more difficult than the reverse computation. And obviously those kind of one-way functions, those get used in things like cryptography, right? So the existence of those is quite well studied in cryptanalysis. So those certainly exist, and those can give you some form of time asymmetry. But arguably, the version of time asymmetry that's relevant for physics is the observer-dependent one. It's the one where you say, actually, for this particular aggregation of microstates and this particular interpretation of that aggregation as this macrostate, this is the computational complexity of the reversal operation, and that is an observer-dependent thing.
You mentioned Penrose, and I want to get to some of your arguments. I don't know if you still have them, but I recall from a few years ago, you mentioned that you have some issues with Penrose's non-computational mind argument. So I want to get to that, but I want to say something in defense of Stephen, that people don't realize what it's like when you're not in academia to, get your ideas taken seriously by academia, and then also what it's like in terms of funding. So people will say that, yeah, sure, Stephen is radamantate or self-triumphant, but you have to be that to the public because that's your funding source, whereas for the academics, they are that to the grant agencies. To the people they're asking for money, you have to big yourself up. It's just that you don't get to see that.
Yeah, I know. I absolutely agree here.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.